So one of the major considerations in organic chemistry is the prediction of products in one major type of reaction class, and that is the polar reaction mechanism, sometimes referred to as the ionic reaction mechanism. What I'd like to do is to go and just show you a quick example. This will be a substitution reaction example that I am going to provide on the screen. So let's say, for instance, we have propyl bromide and we are going to react this with hydroxide ion. And so one of the many questions that we would be expected to answer about this reaction system is, what are the products going to be? In order to answer this question logically and consistently and accurately, we need to identify two major reacting species in the reaction system. One is called the electrophile, which literally means electron loving. And the other species is the nucleophile, literally meaning nucleus loving. Relating this new terminology back to acid and base theory, which we've recently covered in class, electrophiles can easily be classified as Lewis acids, while nucleophiles can be classified as Lewis bases. Recall that a Lewis acid is going to be an electron pair acceptor. While a Lewis base is going to be an electron pair donor. So quite literally, in a chemical reaction, if you can appropriately and correctly identify the most reactive nucleophile and the most reactive electrophile, it tells you precisely how to push the arrows in determining the mechanism of a reaction. Let's put this into practice on this particular example. The most nucleophilic atom in this reaction system is one of the lone pairs associated with hydroxide. This is my best nucleophile. And literally right now, you should circle the most reactive lone pair and place a capital N so that you know that is your most reactive nucleophile. Most reactive electrophile is going to be the carbon bonded to the bromine atom, because the bromine atom is more electronegative than carbon, and so the electron density is skewed such that bromine has a partial negative charge and carbon has a partial positive charge. Now, in actually pushing the arrows, the lone pair from the oxygen atom will attack and make a bond to the carbon atom that is deficient in electron density. In other words, the most reactive nucleophile attacks and makes a bond with the most electrophilic atom in the reaction system. Consequently, carbon, since it can only make 4 bonds, will give up its lone pair to the more electronegative bromine atom, and the bromine atom will be the acceptor of that electron density. Now, in terms of nucleophile, electrophile, Lewis acid, and Lewis base, the Lewis acid accepts the electron pair, so the carbon atom accepts the electron pair from the oxygen atom. Nucleophile attacks the most reactive electrophile, and then the electrophile releases the electrons that it formerly shared with the leaving group to that leaving group. Now let's take a look at some of our problem sets. So let's start with question number 14, where we identify the most nucleophilic atom in the following molecule. Question 15, we're answering the same question. Question 16, question 17, question 18, we're essentially answering the same question. Where is the nucleophilic atom? And let me suggest the following. You're really not looking for the nucleophilic atom so much as you are looking for the atom with the most reactive pairs of electrons that can make a new bond with a reactive electrophilic atom. So let's go back to our canvas and we'll do cyclohexanone and tetrahydrofuran first. So in cyclohexanone, if I draw all of the detail, clearly the best nucleophile is going to be one of the lone pairs on the oxygen atom. In tetrahydrofuran, you really have the same issue. And it really doesn't matter which of these lone pairs you choose. One of those lone pairs is going to be nucleophilic. Let's look at a couple of other structures within the problem set. Looks like we have N-propyl ethenamide, and it looks like we also have the conjugate base of ethene, and it also looks like we have allylic bromide. So let's take these into consideration one at a time. This will be a good time to review some IUPAC nomenclature. N propyl, ethanamide. Now we want to identify nucleophilic centers, but let's just ask the question or answer the question that has not been asked, and that is, which one's the most nucleophilic pair of electrons? The electrons will always be more reactive, more nucleophilic, when they are tethered to the less electronegative atom. So the best nucleophile in this molecule is the lone pair on the nitrogen atom. That's certainly one school of thought. However, it's really important to keep the following in mind. And this is where it gets a little muddy, but it's consistent with what we've previously learned. And with what we've previously learned is that resonance is certainly possible. I have resonance. And since I have resonance in play, I've also got to consider this other Lewis structure. And in this other Lewis structure, I think there is little question that the most nucleophilic electrons are not associated with nitrogen, but rather with oxygen. So I think that, the question that's asked on your problem set simply wants you to identify nucleophilic centers. So you could circle the lone pair on nitrogen or one of the lone pairs on oxygen. But if you really want to know in this molecule which of these atoms would be protonated if there was an acid present, it would not be the nitrogen, it would be the oxygen atom that would be protonated. Now let's take a look at the conjugate base of ethene. And so what I'm going to do is put all of the details in this particular chemical species. And I have one of these carbons bears a negative charge. So on one of these carbons, I'm going to have a lone pair of electrons. It is tempting to suggest that the pi bond is more nucleophilic, but because I have this lone pair on one of the carbon atoms, it is by far the most reactive nucleophile in the molecule. Now you could suggest that the pi bond could also be nucleophilic, but there really is a competition for which one's most reactive, and the one that's most reactive is going to be the lone pair. Finally, let's look at allylic bromide. And you have a competition in this molecule as well. You've got the lone pair, any three of which you could consider on bromine, or you've got the pi bond in this carbon-carbon double bond. Again, the question on this problem set is simply asking you to identify nucleophilic centers. So I think it's entirely permissible to circle the pi bond to indicate that this is nucleophilic, to circle a lone pair on bromine to indicate that this is nucleophilic. If you really want to get down to brass tacks, when this undergoes the reaction with hydronium ion, it's going to be the lone. It's not going to be the lone pair that reacts. It's going to be the pi bond that reacts. But again, to be fair, that's not the question that they're asking. It asks to identify the nucleophilic centers in the following molecule. So this gives you an idea of how you would answer some of these questions. Okay, so let's take a look at a few others so that we can just be productive before we wrap this up. Let's look at questions 19, 20, 21, and 22. Question 19 asks to identify the nucleophilic atom in the following molecule. We have trimethylphosphine. That just brings back warm, tender memories of Breaking Bad, doesn't it? So if we look at this molecule in a little bit more detail, phosphorus, bonded to 3 methyl groups. Just to be geometrically correct, I'm going to go ahead and use dashes and wedges because this actually has a pyramidal geometry. And remember, we have a pretty large non-bonding orbital that takes up a lot of volume. And we are being asked to identify the nucleophilic atom. And that's pretty easy to identify. The nucleophilic atom is going to be the phosphorus atom because of the presence of these lone pairs. So the lone pair of electrons on the phosphorus atom would certainly be the best source of a nucleophile in this particular molecule, and we'll actually, towards the end of this semester, at the beginning of the second semester, look at reactions where this lone pair actually does make novel bonds in organic reactions. We can go back to cyclohexanone and we can answer this in terms of a free response question or in terms of a multiple choice question. So let's take care of both of these at once. Cyclohexanone. The nucleophilic portion of this molecule is simply going to be the lone pair of electrons. But the electrophilic atom is going to be the carbon that is the carbonyl carbon. And the reason for that is that due to the electronegativity of oxygen, electron density is polarized toward oxygen. the oxygen has a partial negative charge, whereas the carbon has a partial positive charge. So the carbonyl carbon is electrophilic. That's going to always be the case where you have a carbonyl functionality. Remember, a carbonyl is not a functional group so much as it is a family of functional groups. So this takes care of 20 and 21. And let's just finish up this podcast by looking at question 22. Identify the electrophilic site of 2-bromobutane. So going back to the easel, the electrophilic atom is going to be the carbon atom that is bonded to the bromine atom, because this will have a partial positive charge. In other words, it is a Lewis acid. Bromine, on the other hand, will have a partial negative charge. It is a Lewis base. So hopefully this allows you to kind of springboard into doing some serious damage on the problem set. I certainly will be talking about this more depth both in class on Monday for section 201 and of course in class on Tuesday for section 202.